In lesson 9.5, we're going to look at classes of functions and the different types of things you've graphed in this class also and in previous classes here. So just kind of an informational piece here, graphs that you need to kind of know the general shape, general types of graphs that will be produced from things. The first one is a constant function, and that's when the graph's going to be a horizontal line. Okay, now notice they say y is equal to a is any number. So in this example, this is y is equal to 1 because it's a horizontal line at 1. It's constant, so it's horizontal. Pretty straightforward. Direct variation is a linear graph, okay, and it is in this form. Y equals ax. We've also used y equals kx when we just did direct variation. The key thing is, if you look at the example of y equals 2x, with direct variation, the y-intercept right here is always 0. Okay, the line must pass through the origin. Okay, there are other lines, but they are not direct variation unless they pass through the origin. So the key thing there, and it's not horizontal or vertical. Horizontal would be a constant function. So the identity function is when y and x are equal. It's kind of a special case of direct variation. If you think about the equation y is equal to x, that's like 1 over 1x plus 0. So it would have direct variation because of the y-intercept being 0, but basically it's a slope of 1. Graphs passes through all the points with coordinates a, comma a. So like 2, 2, 3, 3, negative 1, negative 1, and so on. Okay, that's called the identity function where x and y are equal to each other. And back at the beginning of last quarter, we looked at the greatest integer function. That basically is a step function graph. As you can see, graph looks like steps. Okay, kind of it was a closed circle on the left. Remember, this is where we rounded down to the nearest integer. So its graph looks like steps, and we did that at the beginning of last quarter when we did some graphing stuff. Absolute value, anything with absolute value will be V-shaped if you have absolute value in there. Now this one has kind of the vertex of the V at 0, 0, but you can be at different points depending on if there's numbers added to or subtracted inside absolute value or numbers added to or subtracted outside of absolute value. But anything with absolute value, you can also have upside down V's if you have a negative in front of the absolute values and things like that. But you've done some graphing of absolute value. Quadratics, parabola. Anything in expanded form that's x squared, so this would be expanded form. And remember, if you have it in factored form, so this is to give you an example here, something like that, if I actually multiplied those two binomials together, you would get x squared, you'd FOIL them together, and plus 3x plus 1x, which is plus 4x plus 3. Putting it in expanded form, you'd have x squared. Okay, factored form helps us to find the intercepts with the zero product property and stuff like that. Quadratic is a parabola, though, and if a is negative, then you have an upside down parabola or one that opens down. So you need to know all these, kind of the basic ones, what the shapes are and what the graphs look like. Then we have square root function. Okay, square root function is kind of like a half a parabola. It's an equation. If an equation includes an expression inside the radical sign, so in other words, you have a variable inside the radical, like x, square root function. Its graph is a curve that starts at a point and continues in only one direction. I kind of say it kind of looks like half of a sideways parabola. Okay, remember, if you have a full parabola, that's not a function because it wouldn't pass the vertical line test, but this one would be. And we'll look at some examples later. We just did rational functions in 9.3. This would be an example of a rational function. They can produce hyperbolas. So this would be an example. Two curves is a hyperbola. Okay, where we would have a vertical asymptote there, and we'd also have a horizontal one there, and we looked at in 9.3 some things that produce that. It's where you have for sure an x in the denominator, many times in both. This one is an example of y equals x plus 1 over x minus 1, and again, you couldn't cancel the x's there. So one or more asymptotes and or wholes. Also, when you have a factor that cancels, so this would be if a factor cancels. We looked at this in 9.3 also. If a factor, so like if you had y equals x plus 1 times x minus 2 over x plus 1. So let's say you factored something on the top and into that. Well, now these cancel. Then you would have a whole at x equals negative 1 and then negative 1 something. You'd have to plug that back in. That's not the, for this particular graph with this whole, that's not the function, the rational function that would produce that one, but that would be an example, and we looked at that in 9.3. Inverse variation is a special case of the rational function where the top does not have a variable. So like if you just have a number or a constant on top, y equals 2. In this example is y equals 1 over x, y equals 2 over x. So you don't have a rational function that's got a variable in both the numerator and denominator. Most of the time, if you don't have a variable in the numerator up on top, your vertical asymptote is going to be at 0, and the horizontal one is going to be at y equals 0. Okay? And that's what they're saying right here, that the asymptotes would be there. That's still a rational. It's an inverse variation function. It's still a type of rational function, just that the function on top is a constant function or a number. So, using all those graphs, we're supposed to identify the type of function represented. This is half a curve, so if you look up to this one, you're just identifying it. This would be a square root function. Okay, it's kind of a half of a sideways parabola. This would be naming it a rational function. If you wanted to get more specific, you could say rational function with a whole. Okay, but rational function is fine. Okay, let's look at this one. Emily launched a toy rocket from ground level. The height above the ground level, h, in feet after t seconds is given by this formula. Okay, notice this key thing here. We've got the variable squared. It's not an x, it's a t here. T squared. That tells me right away, it's in expanded form, that tells me quadratic. We've got the variable squared, not scared. Quadratic, which produces a parabola. So which of these graphs is a parabola? Notice it would be this one right here. So that would be the answer, letter B. Why is it an upside down parabola? If you look out in front of the t squared, we have a negative 16. Anytime it's negative, the parabola is going to open down. Okay, so here we're supposed to identify the type of function and then graph it. So this is, if you look at it's got absolute value in it, so it's absolute value function, so that would be identifying it, absolute value function. And we're going to make a table. Now this automatically absolute value function tells me it's got to be V-shaped. What I suggest doing is making a table. Okay? Now we got to get to the V. We got to have a couple points on either side of the V. Let's start out with negative 2, negative 1, 0, 1, and 2. Okay? And this one's pretty easy. I'm not going to pull it up necessarily on the, you could put it in the calculator, but let's make a table. Let's put negative 2 in. So if I put negative 2 in here, I take the absolute value of it, which is 2, and then I subtract 3. So that's going to be negative 1. So at negative 2, we're right here at negative 1. If I put negative 1 in, so I'd have the absolute value of negative 1, and then subtract 3. So it'd be 1 minus 3. It's going to be negative 2. Then I put 0 in. Absolute value of 0 minus 3 would be, so it would be 0 minus 3, which is negative 3. If I put 1 in, absolute value of 1 is 1. Subtract 3, it's negative 2. So now we're starting to V with those repeated values there. If I put 2 in, the absolute value of 2 is 2. Subtract 3 would be negative 1. So let's finish. I already plotted negative 2, negative 1. Let's plot negative 1, negative 2. Then we have 0, negative 3. 1, negative 2. so on. You can see there that the v goes like this then. Anything with absolute value is v-shaped. It's got a radical in it, so it's a square root function. So we're identifying it. So make sure in the assignment when they say identifying graph that you name it from the ones we just reviewed. Okay, let's make a table. Now, point out, now the last one with absolute value, I know it was v-shaped, so I tried some negatives for my x. Here, notice if I tried a negative. If I put a negative in for x, I take 4 times any negative number, I'd have a negative under the square root. Well, we can't take the square root of a negative. That is not a real number answer. So your table here, you're going to start at 0. Because it doesn't make sense to put negatives in there because I'd have a negative underneath the root. Now, if that 4 was negative in front of the x, then it might make sense to put some negatives in. But it's a positive, so I got to multiply by, we could start at 0 because I can take the square root. So if I put 0 in, I have the square root of 4 times 0, and then subtract 2. Well, that's the square root of 0, subtract 2. 0 minus 2 is negative 2. So at 0, we're at negative 2. If I put 1 in, I have 4 times 1 underneath the root, so I have the square root of 4, subtract 2, well that's 2 minus 2, so when I put 1 in, I get 0. So at 1 comma 0, I'd be right there. If I put 2 in, okay, I'd have the square root of 4 times 2, and then outside the radical I have subtract 2, so it'd be the square root of 8, subtract 2. Now, square root of 8 doesn't come out to be a whole number, so I would just suggest approximating it. The square root of 8, I'm not sure what that exactly is, but then when you subtract 2, I do have that down. It's about approximately 0.82. So you take the square root of 8, which is going to be 2 point something. It's about 2.82. And then you subtract 2, so it's about 0.82. So at 2, we're going to be at about 0.82. So this is where it becomes an approximation. Okay, if I put 3 in, I take the square root of 4 times 3, and then I subtract. So the square root of 12, subtract 2. And I do have the final answer down. Square root of 12 would be 3 point something. I think it's about 3.46 or something like that. And then subtract 2, so we get about 1.46. So about 1.46. So at 3, we're at just shy of 1.5. And then let's do one more. Let's put a 4 in. Now I'd have 4 times 4 underneath the radical, that's 16. The square root of 16, and then subtract 2, so that's 4 minus 2, then I'd be up at 2. So, and that's enough points to be able to graph. It's basically going to look like that. Okay, square root function, kind of a half of a curve. Starts at a point and goes that way. Alright, this is a rational function. I've got x's on the top and on the bottom. So rational function, we graphed a lot of these in 9.3. So a rational function, we're going to factor the top. That's a difference of 2 squares right here on top, so it factors into x plus 3 and x minus 3. And I have x plus 3 on the bottom. Now we have a factor that cancels. This creates a whole. And if I actually set the factor that canceled equal to 0, subtract 3. So x is negative 3, so I know it's negative 3 comma something. So if I actually look at my simplified expression, I have just x minus 3 left. So what you would do, so it's y equals x minus 3 here left after I cancel. If I actually put negative 3 in for x, negative 3 minus 3 is negative 6. So here's where my whole is, at negative 3, negative 6. So we're just going to put an open circle there. And then let's see what happens. So if we make the table, At negative 3, we're at negative 6. That's a whole. And then pretty much after that, I'm going to pick some on, so let's go with negative 4. I would put it into the simplified expression. If I put negative 4 in here, negative 4 minus 3 is negative 7. So negative 4, we're at negative 7. Negative 2, I do negative 2, subtract 3, be negative 5. At negative 1, it'd be negative 4. So we're going to be right there. So it's going to be, oops, I didn't draw that line very good. It's going to go like that, and then it's going to go like that with a hole at negative 3, negative 6. And we graph some of those in 9.3. So make tables for them by plugging in the values. And that's it for lesson 9.5.